Following is my conversation with Bogdan-Ionut Krista. Bogdan is a researcher at the junction of artificial intelligence, natural language, neuroscience. His research work is focusing on theory of mind and how AI system designers, AGI system designers, and autonomous system designers should think about theory of mind as a necessary ingredient to train AI models, as a necessary step for human-machine interaction, a machine that has those AI-powered autonomous skills. I find this conversation very refreshing, very original. Bogdan brings a lot of unified perspectives to the table. He made a pretty elaborate presentation in this conversation as well, which is very practical. It makes you think a lot of questions. I had a lot of fun having this conversation with Bogdan. Hopefully, I'm going to talk with him more often, do some collaborations as well. Now, here is my conversation with none other than Bogdan-Ionut Krista. Bogdan, how are you, sir?
Good, thanks. How about you?
Very good, very good. As we were just talking a few minutes ago, I am, Bogdan, just fascinated with your work on theory of mind and how you are connecting the dots and bringing that field into AI and AGI and asking all the right questions. So maybe, a good place, Bogdan, to start is you have a very impressive, fascinating background. Let's maybe start there, that how your journey got started. And so let's start there. And then I think from there, let's then get right into what is theory of mind. But let's first start, sir, with you.
Sure, thanks for the kind words. So I have a background as a computer engineer. I have a bachelor's in computer engineering from Polytechnic University in Bucharest. And then I got a master's in machine learning in France, followed by a PhD in deep learning and a bit of quantum machine learning, applied handwriting recognition, also in France, so at Telecom Paris. And yeah, I've been fascinated by this idea of super intelligence at the same time, like the problem of how to control it and like how to align it with human preferences and objectives, at least since like 2014, when Nick Bostrom's book Super Intelligence came out. So that's when I started thinking about that a bit more seriously. But I have to say, for a long time, I kind of felt like this might be quite far off. Like maybe it's like I didn't feel necessarily a lot of urgency, and I also didn't feel like I could contribute that much. So I felt like I might be able to go through all the academic process of becoming a professor, and I might not need to worry about AI safety until a much longer time, until much later. But actually, as I was going through my PhD, I kept seeing like all the progress in AI, and I kept feeling like, okay, this might happen sooner than I thought it would. So it might be the time to start trying to contribute myself something to this, or at least learn about it. So that's how I got to work on what I'm currently working on, which is I'm working on machine theory of mind at Oxford Brookes University with Professor Fabio Puzzolin, and also with collaborators from Cambridge, so Professor Barbara Sahakian and Dr. Christelle Langley. And theory of mind is this capability that humans have, and maybe also some other animals have to a lower degree, of like inferring others' mental states. So it could be things like beliefs, feelings, preferences. And I'm particularly interested in inferring preferences because like the more powerful AI becomes, the more we would want it to both be capable of inferring human preferences and be like motivated to pursue them, basically. So I think this is absolutely crucial for powerful AI. This is a capability and the motivation that we would really want powerful AI to have.
That is awesome. That's awesome. So, Bogdan, tell us a little bit more about how theory of mind have developed. It looks like there are different paradigms, there are different frameworks. Some frameworks are more popular than others. But how to, think about it. So I think let's maybe take a deeper dive into. And as I was sharing with you, I was reading your fascinating paper. This paper on knowing me, knowing you, theory of mind in AI. It's a fascinating read. So tell us a little bit more about the different frameworks and how their pros and cons uh, and how to think about it. If somebody is developing AI, whether narrow AI or AGI technologies, how to and somebody wants to study theory of mind, you know, how to go about that.
Yeah, so I think to a large degree, this is kind of an unsolved problem, unfortunately. Though it also makes it kind of exciting to work on. So there's a lot of stuff to work on there. I think there's like the cognitive science and neuroscience side. So like theory of mind is this concept which like started in cognitive science when people started looking at what other primates might be able to do, like whether chimpanzees might also have these capabilities. But there's also work in machine learning. So like one important strand of research is the whole area of inverse reinforcement learning, where you it's kind of like literally the inverse of reinforcement learning. So while in reinforcement learning you are given a reward and you are trying to like learn a policy which like maximizes that reward. In inverse reinforcement learning, it's kind of the opposite in some sense. So you're given a policy, you get to see some behavior, and you want to infer like what was the reward which that policy was trying to maximize. So there are multiple strands. Now I think like what motivates our project is the fact that as I said, this is still like an open area. It seems to me like a really important problem. And it's also like we don't know how humans do it. We don't know how to do it in machines. It kind of felt like we might be able to get some inspiration from what humans do and try to implement that in machines. And also like the other way around, we might get to test like some computational models and see if humans seem to be doing something similar to computational models we would propose. So it's still ongoing work. We don't have, unfortunately, like any final solutions or anything like that. But I think it's fascinating and also really important.
How do Bogdan, maybe one thing to talk about is how do we as people build the theory of mind models for other fellow human beings? Uh, how do we do that in our? Is it something we are doing? Which part of brain is involved, and are there any frameworks or models as to how people do that? I always kind of Bogdan, think about that at some level. AI and AGI is a way to reverse engineer human mind, that there are capabilities that we have, and we are trying to see if we can reproduce them and re-implement them even in a better fashion in machines. But how do we as people, how do we do that? Get into each other's mind or run those simulations in our head that what other person might be thinking. Tell us a little bit more about it.
Yeah, so I have to like preface all of this by saying that I'm not, I'm not an expert in what humans do, unfortunately, though I have some, like I interact with people who know more than me about that, and I know some of the literature. Like my understanding is that currently we know some of the brain areas which are involved in theory of mind. So there are like, people know about stuff like this, like the RTPJ, tempoparietal junction. So we know some of the brain areas involved in that. My impression is that we don't have, like, there are some abstract models like inverse reinforcement learning or something else called Bayesian theory of mind, where you kind of try to apply Bayes theorem and like Bayesian models to like try to infer beliefs from behavior or preferences from behavior, from observed behavior. But my impression is that we don't have like a full theory of like going all the way from like these very abstract principles of like inverse reinforcement learning or Bayesian theory of mind, all the way to like precisely like which neurons implement what in the human brain, and like can you write all of this down, and like can you code it, and would you get human like theory of mind? We are not there yet, unfortunately. So yeah, that's like a very high level view. Like you mentioned simulations, and I think yeah, I think that that's also a very important aspect which we discuss a bit in the paper. So it's this idea that we humans seem to like simulate what others think by like things like empathy and processes like putting yourself in another person's shoes. Um, so yeah, I think like, and that's called like simulation theory of mind. I think we're still trying to like figure out exactly what's happening there. Those some ideas, like you can connect those ideas to stuff like model-based reinforcement learning, where you also have simulations and so on. So you can draw connections to other theoretical ideas, but I think we are not, unfortunately, we are not at the stage where we know very precisely exactly what's going on. So that's like my
No,
understanding.
that is so spot on. And certainly, we as people, even to your point, I mean, we do this all the time. It is tacit knowledge, but even we can't explain that how we do that. And it's not as if that we are perfect mind readers and modelers of other people's minds. I mean, we as people misread the situations all the time, and look at all the problems in the world that arise from building incorrect sort of theories of mind about other people, other societies, cultures, countries, all that stuff. So it's a super duper uh, important topic. In your paper, you also reference to that how it connects with uh, autonomous AI systems. You quoted Tesla cars or autonomous vehicles uh, and deaths of pedestrians and whatnot, and a algorithm goofing up, not knowing what to do. So the topic certainly is very important, and in terms of its uh, ethical and other implications. Some of your slide decks that I saw, Bogdan, where you talk about intent-based models and other more deeper models, maybe it's a good time to take, if it's okay with you, to take our audience through that slide deck of yours and kind of, I want people to see this framework and this thinking through your eyes.
Great. So yeah, this is a slide deck from like a recent presentation of mine, which is called AI alignment, the biggest problem many people haven't heard of. So like I discuss here how powerful AI could be a really big deal as some kind of like motivation, how it looks more likely than not that it might happen this century, and like more than 10% probability that it could happen within the next couple of decades, and then how we need to like figure out how to handle this transition toward with powerful AI. And like one part of this is trying to solve this technical problem of aligning AI with human preferences. So this is like the technical AI alignment problem. And then how at least one line of reasoning suggests that this might really be the most important problem we face this century. And I have to say that all this, like all these slides are inspired by this blog post from Holden Karnofsky. And I highly recommend this this series of blog posts, which goes into many more details than I can go.
I agree with you, Bogdan, that there is a really good chance that AGI will happen in this century, and we need to start thinking about these things now and not later, because we almost have to build AI with theory of mind and other things in it so that we are able to uh, communicate better. We both know in order for an AI to be successful, it has to be predictive and generative. It cannot just be reactive. It cannot just be reacting in time and say, okay, Amjad said this or Bogdan said that. What is the most plausible reaction? It has to be a lot more than that. It has to kind of, have that broader history and models and being able to predict, what, people are thinking about and that kind of a thing. And maybe even ask questions and things like that, the way, we as people, we infer, but then, we ask clarifying questions and we take corrective steps. So I am again just fascinated.
So yeah, I try to make the argument here that powerful AI could be a very big deal, and like one way to think about this is that we could build AI which might be able to fully automate innovation. So like we know that humans are capable of like scientific discoveries, of technological discoveries. So in principle, AI might be able to do the same. And especially if you were able to build the kind of AI which would take humans out of this feedback loop of producing innovation, like you could get a much faster feedback loop. So feedback loop where just by getting more, by putting more resources into building more AIs, you would then get more ideas, and this could lead to more resources, and you could just have a very fast feedback loop with no humans needed inside there. And
this point that Bogdan that you make on your slide, that if we have a real opportunity of expanding beyond planet Earth, in all likelihood, since we as people are very Earth-centered and very fragile, it is going to be in all likelihood our AGI and technology that is going to go out there and do all those things. Now, of course, we will have some physical or virtual presence as well. But this point is very valid that uh, uh, it is going to be our AGI tech that is a lot more likely to leave Earth and go out in other parts of the solar system or galaxy. So very important point that you are making here.
Yeah, I completely agree with that. That it, yeah, AI seems much more, how should I put it, non-fragile, much more robust to conditions like outside of the planet Earth. So yeah, I completely agree with that. So the point of all this is that this could lead to much faster economic growth. So you could imagine yearly GDP growth like increasing 10 times from like 3% to like 30%, which would be like, economies doubling every couple of years, which is much faster, like kind of a crazy world. And of course, if you take like if you have AIs innovating on much faster, at gigahertz frequencies, you could also have much faster scientific and technological discovery. So all of this is not just that it could happen eventually, but like once it starts, it could accelerate everything. And we could be in a kind of world which is much less predictable and which moves much faster. So I think this is like motivation to also think about it in advance and try to think hard about this.
Yeah. And one thing
Um,
Bogdan, I'll say is the reverse is also true, meaning the AI has to have a theory of mind on us. We need to have a theory of mind on the AI and machines. We also, as people, need to know that what it is really thinking about, really doing, because if it is too black boxy and you never know what is really going on, then we would be in the same sort of disadvantaged situation because uh, something that is equally intelligent or more intelligent than us, uh, they can outsmart us, they can you know sort of deceive us and all those things. So all those questions become very important, right?
yeah, I completely agree. So like this touches on subjects like interpretability and explainability. And yeah, like I think this is also kind of like the dark side of theory of mind. So like theory of mind allows you to infer preferences so that you might be able to like fulfill them. But it also like you need theory of mind to deceive somebody. So
Yeah.
this comes to that aspect of like motivation, like not just having the capability to infer preferences, but like the AI also being motivated to follow human preferences. Yeah, so like related to this, there's this idea that this transition to powerful AI could happen soon. So of course, so I mentioned here an expert survey. Like, of course, there's a lot of uncertainty about in this survey. So it doesn't mean that it's necessarily right, that the figures here are necessarily what's going to happen. But this is a survey from a few hundred AI researchers from two of the biggest conferences in machine learning, NIPS and ICML in 2015. And one of the questions in the survey was, when would unaided machines be able to accomplish every task better and more cheaply than human workers? And if you look at the estimates, the probability estimates, it came to about 20% that this would happen by 2036, so in about 15 years from now, about 50% in roughly 40 years, and about 70% by the end of the century. Though coming back to this idea of uncertainty, like they also asked a slightly differently phrased question, which was something like replacing all the jobs instead of every task,
Yeah.
where you can kind of like decompose the job into tasks. And there they gave like longer timelines. So I think it was something like instead of 2060, they gave like 2100 or something.
Yeah.
So of course, like as I mentioned, this has to be taken with some salt, some grains of salt. But I think it's evidence that these are not outlandish concerns that like no AI
No.
researcher is taking this seriously. There are uh, there are quite a few AI researchers thinking this is a plausible concern this century and even within
Yeah.
a few decades.
Very much so.
I also mentioned this forecasting framework, which I find very interesting and probably the most thorough work I've seen on like trying to think rigorously about like when powerful AI might happen, especially powerful AI based on methods similar to those we have today, like stuff like deep learning or reinforcement learning. So in this framework, they try to address the question, like based on the usual patterns in how much AI training costs, how much would it cost to train an AI model as big as a human brain to perform the hardest tasks humans do? And when will this be cheap enough that somebody might be expected to do it? And here the numbers they come up with, and I'm gonna go into more details, like how exactly they come up with these numbers. They are actually very similar to the previous ones, the ones from the survey. So more than 10% in about 15 years, about 50% in some 35 years, and about 80% by the end of the century. And I also think this is very interesting because, as they mentioned, this could provide, like their framework could provide an explanation of how at the same time, like AI systems from more than 10 years ago didn't seem very impressive. The AI systems of today seem more impressive, though they still fall very, very short of what humans can do. And at the same time, the next few decades or the next 15 years might lead to powerful AI, like the kind which might automate innovation. So like their basic explanation for this, like one potential explanation is basically you need to use similar amounts of compute to what the human brain uses. And if you don't put in that much compute, you're just not gonna get to transformative
Yeah.
AI. And this is how you could explain all of it. Like this is one potential explanation for all these points. So yeah, like this framework used extrapolated this recent empirical discoveries of this phenomenon called neural scaling laws. So there are a bunch of papers from OpenAI and now more from more people. Here they were looking at language modeling. So you're just trying to predict the next word in some text. And they were looking at how the test loss changes as you change the amount of compute you use that training time. And what we basically saw is that you can vary the amount of compute used by like 8 orders of magnitude, which is like 100 million. So it's like a huge variety in the amount of compute you use, and still like the neural scaling law seems very stable. Like it's almost a line on a logarithmic plot, and you can basically come up with like a power law for how this seems to happen. And basically, if you extrapolate this kind of thing and with some other assumptions, you get to like the predictions of when it might happen, of when powerful AI might happen. So another thing, another phenomenon which contributes to this is just the amount of compute which people have been putting into the biggest training runs. So if you look at how compute has evolved from 2012 to like 2018, there was an increase of like 300,000 times. So almost 10 times more compute every year. So people are just putting more money and more compute into training big systems.
Yeah.
And related, like there's a similar phenomenon with language modeling, with language models going on. So like the most recent language model, really big language model just came out this week. I think it's 500 billion parameters, more than 500. And like just 3 years ago, it was 100 million parameters.
Yeah.
So all these trends are contributing to this this forecast. Also, algorithmic progress. So here, if you just keep fixed the level of performance you require on ImageNet, and then you look at how much compute you would have needed in 2012 with AlexNet, and then around 2019 with a version of EfficientNet. Like this has also gone down by 44 times.
Yep.
So yeah, basically when you put all these things together, like when you try to estimate how much compute people might be willing to put in, how much the efficiency of the algorithms might keep improving, and how much the cost of compute might also go down by like extrapolating more slow or like slow down versions of it. Like you come up with like the main thing in this plot is this black line, which is kind of like an average of multiple ways of thinking about this, which is exactly the estimates I mentioned previously, which are something like 50% by 2055, something like between 10 and 20% by 2035, and 70% by 2100.
Yeah.
But like that's kind of like an average. Like you can, if you make, depending on more aggressive or more conservative assumptions, you'd come up with different estimates. So like
Yeah.
if you think that language modeling is all you need, so if you think that just by scaling up GPT-3, like GPT-10, say for example, might get you to that AI which fully automates innovation. If
Yeah.
you buy that hypothesis that that is plausible, then you get much faster timeline. So the 50% would come at around 2035, and the 30% would already come by 2030. So
Yeah.
if language modeling could be enough, like this could be really fast, could be in the next few decades. On the other hand, if you think that you might think something like, oh, all the algorithms we currently have are, none of them would take you to human level AI or to transformative AI, like no matter how much compute you put into this. But that kind of assumption seems like there don't seem to be very good reasons for that. Because you can look at evolution, which is a pretty dumb algorithm which still produced human level intelligence because it produced humans. And like if you look at estimates of how much compute evolution used by trying to estimate how much compute a brain uses and like how many brains there existed since the beginning of time until now. And then you also try to extrapolate like how much compute we might get by the end of the century. You get to something like 50% probability that we are going to get that amount of compute. So
Yep.
you might be able just to like very stupidly just emulate evolution on a computer and still get to human level AI like this century. So even if
And
you're
it's a
very
very
conservative
important,
in your assumptions.
yeah, I think that's a very important point, Bogdan, that you are making, that uh, human evolution, that Darwinian selection algorithm, uh, while it is elegant, it is also pretty simple. And uh, you can brute force your way into AGI as well. That it is less about how smart an algorithm is, it is more about everything else around it, you know, the data, the compute, the embodied cognition, all those things. So that's a very important point that you are making, drawing this parallel and this analogy with human evolution. I really like that point.
So yeah, going like into more details about this idea of scaling up the GPTs, for example, just scaling up natural language processing. I want to highlight this article that recently came out in Neuroscience, where some machine learning scientists give their opinions on whether this could happen, and there are at least a few pretty well-known machine learning scientists who really think this might happen within a few decades. So, for example, you have Professor Sam Bowman, who came up with colleagues came up with these natural language processing benchmarks like Glue or SuperGlue. And he says that he believes that just by scaling up current methods, especially after you get some more compute improvements, you might get to human level language behavior within a decade or two. So again, coming back to this idea that this is starting to look more and more plausible, even like soon.
Yeah.
And somebody else from Google Brain giving like estimates of training compute budgets of 10 to 100 billion dollars, which is not cheap, but like it's on the level of the Large Hadron Collider, which might also get you to like solving pretty much all language tasks.
Yeah.
And I also want to highlight this other this AI alignment newsletter on the scaling hypothesis, which which goes to more evidence for like scaling up, leading to increased like improved performance. Like there's a lot of work coming in the last 2 or 3 years at least, which shows that you often get surprising gains just by putting more compute into existing methods. So yeah, from here I think I'm gonna go to the AI risk argument. So like if this might happen really soon, like I think it's worth really thinking hard about what the consequences might be. So there have been AI risk arguments from many influential computer scientists, starting even close to the birth of the field of AI. So this is Alan Turing in 1950, saying around 1950, saying it seems probable that once the machine thinking method had started, it would not take long to outstrip our feeble powers. At some stage, therefore, we should have to expect the machines to take control.
Yeah.
So basically, coming back to this idea that if you build something really intelligent, maybe more intelligent than you are, it seems like by default it would not be easy to control it indefinitely. So probably need to think hard about how to do this.
Yep.
So I also mentioned here this idea of existential catastrophe. So an existential catastrophe could kind of comes in three types. One of which is would be human extinction. Another one might be an unrecoverable collapse of human civilization or an unrecoverable dystopia. And what they have in common is this idea of that humanity's long-term potential would be destroyed. And by humanity's long-term potential, what is meant is that this could be really big. Like, depending on what assumptions you make, like if you think that humanity might survive for 1 billion years just on planet Earth, and like the population would stabilize to just 1 billion people, you would still get a huge number of people. Like you could get a number with 16 zeros. Like if you believe our future could be even bigger by, for example, if we manage to get the technology to colonize the universe, then you get something with 32 zeros. And if you think that human brains might be emulatable in computers, then you get a number with 56 zeros. So like the stakes are literally astronomical. Like the future could be really big, and it might also be really good if like current trends, I would say, like human life seem to have improved recently. So if current trends hold up and we don't destroy ourselves in like one of these three ways, for example, like we could have a really long future ahead of us with a lot of human lives and potentially happy human lives. So some people have tried to estimate, in particular, Toby York, who is a philosopher at the University of Oxford, have tried to estimate like what the total existential risk during the next century might be from different events. And the numbers he's come up with, which of course are like probability estimates. So again, there's uncertainty about this, of course. But he came with numbers like 1 in a million for an asteroid impact, 1 in 1,000 for nuclear war or for climate change. And actually the highest, like the riskiest event, he estimates would be unaligned powerful AI, for which he gives like a 10% probability. And given that the total existential risk for this century, he puts at like 16%, like unaligned AI would have more than half of that. And like, even if you're skeptical, even if you think, okay, maybe he's just a philosopher, maybe he isn't as familiar with machine learning methods as others. Still, if you look at the same survey I mentioned previously from AI scientists, they were also asked about existential risk from AI, and they came with something like 5%. So not a huge difference, I would say. So again, for me, this is like, all this is to say that this looks plausible, unfortunately, and like the most rigorous thinking I've seen on this, it seems like this could really happen. Even if you like don't buy these arguments about the long-term future and how big the future could be and how good it might be, even if you only take into consideration like currently living people, it still seems commonsensical to try to reduce any like potential existential risks. So, for example, if you make a back of the envelope calculation of how bad would it be if like just all of the people in the US, currently living people in the US die? How bad would it be if you try to like quantify it with money? So the US government seems willing to spend up to $4 million per life of an American. So like if you add up all the US citizens, that you come up with something like $1 quadrillion.
Yeah.
And then if you believe that the risk of human extinction over the next century really is something like 16%, for example, then it would be worth spending more than 2 trillion just to reduce that by 1%. Just if you just count the American lives
Yep.
you would save. So if you don't count all the people currently living, if you don't count anybody in the future who might have it. And this some people think, and I would agree, that it seems plausible that you could get this risk reduction of 1% with much less than 2 trillion. So seems like this is pretty neglected. So one framework to like think about how impactful different global problems are and evaluate AI risk according to this framework is to think about the scale of problems, their solvability, and their neglectedness. So scale would be basically if we solve this, how good would it be? And in the case of AI risk, like the risk, this evaluation also puts the risk at about 10% in the next 100 years. Solvability would be something like if you double the resources you allocate to this problem, like what fraction could you expect to solve? And this evaluation was, of course, highly uncertain, but they expected that if you double the efforts, you could reduce the most serious risks by around 1%. And related to this, neglectedness, which is how many resources are already going towards this. This problem for AI is like at the time in 2017, they were estimating on the order of $100 million per year, both for technical and policy approaches. So if you just think about the technical approaches, it's less than that. So they roughly estimate that if you put in $200 million every year instead of 100 million, you might reduce the risk by 1% already, which seems doesn't seem like seems like cheap compared to like the risk.
Yeah.
Yeah, I also mentioned briefly like how you might think about alignment, this alignment problem.
I think this point speaks to your theory of mind work as well, that it comes from that literature. So I think this would be awesome to go into these different types of alignments, intent, outer, inner, and what is that journey looking like?
Yeah, so as mentioned here in this slide, like if we think about the entire alignment problem, like it's a bit hard to pin down because there's no consensus on many different things. Like we don't know exactly how powerful AI is gonna look, like how it's gonna be built, who is gonna build it, how is it gonna be deployed. So it's not easy to pin down, but it should imply that AI systems are safe to use. And one way to like one slightly narrower problem, slightly narrower part of the entire alignment problem is this idea of intent alignment from Paul Cristiano, which is that the AI tries to do what the programmers want it to do. So intent, of course, is very relevant for theory of mind. So one part of theory of mind is trying to infer others' intent. So I think this is very relevant. And you could decompose intent alignment into outer alignment, which would be trying to align what the programmers want to what they actually code in. So like the objective function or the loss function or the reward function in machine learning or reinforcement learning. And like one failure mode here could be if the behavior you get is actually bad, like it's not what you actually intended, but it looks good according to the reward function you programmed in. So if you're programming a bad objective, you're probably not going to get what you intended to get. And then there's inner alignment, which is basically making sure that the policy you get is really robustly pursuing the objective. So it's not just at training time, but also, for example, at test time, if you get some distribution shift. So like like bad behavior of distribution is one failure mode, and one analogy could be humans and evolution. So if you think about humans, we came out of this search process of evolution, and I'm gonna anthropomorphize a bit evolution, but you could think of evolution as like maximizing the objective of the number of surviving descendants you could have. So like evolution kind of wanted to train us to do this, but that's not what happens. So humans don't just optimize for the number of descendants they are gonna have. We also care about happiness and art and all things like this. And some people don't care about having descendants at all. So this is like an example of an inner alignment failure, where you have an objective which the optimizer wanted to like have you maximize, and what actually happened was that we humans are not robust of distribution. Like our current environment is different from the ancestral environment. So in the ancestral environment, it kind of looked like we had to produce offspring for the human species to survive. But now that the kind of like distribution has changed, like the environment has changed because we have changed partially. We are very far from pursuing this objective of just maximizing the number of descendants we have.
Yep. Do you see Bogdan in this in intent and inner and outer sort of alignment models? Any game theory or different agents or behaviors, whether they are rationally acting or irrationally acting? Do you see an application of those game theoretic models in this as well?
Yeah, I think it could be especially relevant. I mean, especially if powerful AI is produced through something like multi-agent reinforcement learning, then it seems like game theoretical analysis could be really important to try to like figure out like, I don't know, what the equilibrium might be. Like I've been thinking about a bit about like how phenomena like psychological altruism, like caring intrinsically and like for ultimate purposes about another's well-being, how this might have come out. And like there are some mathematical analysis and like game theoretical analysis of things like this. Well, it's more about biological altruism, which is a bit different, but I do think it's there probably are some fruitful lines of analysis related to that. So I'm gonna this is very useful for the video version of this. For the audio version, I'm gonna try to explain it still. So it's this example of this Coast Runners game, an agent trained to play this game called Coast Runners. So what the programmers intended here was for having a boat which goes through a race as quickly as possible. And to try to get the boat to do that, they put in some like blocks of rewards. So what actually happens here is that the boat basically finds another strategy which gets even more reward, but which is totally different from what the programmers intended, which is for the boat to finish the race. So it basically goes through a loop and collects a lot of points by doing that, and it also catches fire because it crashes into other boats. So this is an example of how if the reward you code in is not actually what you intended, then you can get really unintuitive behavior from your agent. And that's not, so in this case, it's not because the boat is not getting enough reward. It's getting more reward than it would have gotten if it really went to the race. So this is really the optimal behavior according to the reward you programmed in. So basically,
What
this
a
is what happens if you do.
very powerful simulation, the law of unintended consequences.
Yeah, basically, if you don't think hard about what your reward incentivizes, you might get really unexpected results, like catastrophically bad even.
Yeah.
And for inner misalignment, I have another video. So in one of the maze environments at training time, there's some cheese which at training time always happens to be in the right hand corner of the maze. So at training time, the agent you train becomes good enough that it gets to collect the cheese. So you might think that I'm going to try to show it again. You might think that it actually learned to go for the cheese because at training time it always gets the cheese. But if you test it then by moving the cheese to random locations at test time, we're going to see that what it actually does, what it has actually learned to do, is not to go get the cheese, but to go to the top right corner. So the idea here is that if you have spurious correlations in your environment, and of course this is a toy example, but like you can have a lot of spurious correlations between your objective, the objective that you truly intended, and something else which is not really your objective. And like this is a powerful example, I think, of kind of like the worst case thing you could get. Like you could get an agent which has very robust capabilities, which in this case corresponds to being capable of navigating the maze.
Yeah.
But doesn't have a robust objective at all. So the objective has learned doesn't generalize. And you can imagine that the more powerful AI you get, the more dangerous this scenario becomes, where the AI is really good at doing things. It has very robust capabilities, but it really didn't get what you wanted it to do. Or at least it's not motivated to do it.
Yeah.
It's doing something completely different. There are also a few more examples. Like another example is where you have at training time you have this yellow diamond, and again the agent seems to be going to the yellow diamond. And you might think, like, if you have then at test time you have an orange diamond and the yellow star. If you think about a human, for example, you might think that the human would go get the diamond, because it seems intuitively that humans care more about shape than about color. But what happens with the agent is that it goes after the color. So it goes after the yellow thing, after the yellow star, not after the orange diamond.
I think this is to your point, Bogdan. It's all about having a model of the world. And if the AI does not have a model of the world, then these types of behaviors will emerge because it does not have all that other information that we as people do.
Yeah, but I have to say that it's not, like, in some sense, it's kind of worse than that, because like the model of the world could be like, like how you're gonna move from one piece of the maze to another. And in some sense, it has this because it's able to navigate the maze. Like it doesn't get lost. It goes like robustly to the top right corner, for example. But what happens is that it doesn't have a good representation of the objective. Like its representation of the objective is not robust at all. Like, or at least it's not what we intended it to be.
Question, Bogdan, for you. In a reinforcement learning situation, the example that you were giving a minute ago, let's say you trained it on a yellow colored diamond and it got a reward or whatnot. And now you are randomly shifting the location of the diamond in the maze. You also have changed its color. And you have created these distractions with other yellow colored objects and whatnot. In a good algorithm that is not batch mode, just batch mode training, where continuous training can happen, if it runs into a yellow object and gets no reward and tries to run it again and gets no reward, and then its algorithm of explore versus exploit says, well, let's go try something different. And it stumbled upon that orange diamond, and now all of a sudden it gets a reward. If learning is happening online as opposed to the batch mode, then probably I would imagine that it will pretty quickly relearn. And then from there, if it has the learning of what it learned before and what it learned now, both in its memory, then next time you create more distractions, I think it would be able to behave better. I think the some of this issue, Bogdan, I think, is that in these examples, we are assuming batch mode training. You have been trained once, no new training. Now you just, you are a no new training happening. You are just an automaton, go out there and then just deal with it with training that has happened before. So I think the once we move from the batch mode training to just saying, okay, I am learning all the time as an agent, I hope that some of this dynamics and behaviors will maybe somewhat go away.
I mean, I agree with that, and there have been like there's even some theoretical work showing that in the case of Bayesian reinforcement learning, I think you can make some of these problems go away if you do online training, in theory at least, like if you do enough of it. But and also like including in this paper, they've shown that if you do train on a larger distribution of environments, like if you do shift the cheese location at training time, it does become robust and it does go to the cheese. But the point was not that that we don't know how to solve the problem in these simple environments. Yeah. The point was that we don't know for sure how to solve the problem in general environments.
Yeah, the misalignment of objectives. Yeah.
And also, I have to say about online training, like I do think it's very interesting, and I do think it's promising. But on the other hand, it comes with like it comes with the cost of needing to have a human in the loop. And like you can imagine that there are going to be incentives like profit incentives or like latency incentives where you really can't afford to have a human in the loop, or it's much cheaper not to have a human in the loop at least. So that's another issue, I think.
No, very smart point. Very smart point.
But just to summarize, so like the points I was trying to make here is that powerful AI could be a really big deal. Just even also in terms of the future and in terms of the currently living people who might be affected. That it looks likely to happen this century, though of course there's quite a lot of uncertainty, and it could happen really soon, like in a few decades. That we need to figure out how to manage this transition, and we also have some technical problems which are not solved. One of them is the technical AI alignment problem. That this field seems very neglected, so there's not that much money currently going into it. There aren't that many people. Like there are probably less than 1,000 people working on it. This is like an opportunity to really try to make a difference. Though of course, like there's also some caution required because we don't really understand very well this problem, like what we are going to need to solve. And I and at least a few others think that this really could be the biggest problem with this distinction.
No, I'm totally with you on this one. So let's maybe talk about, Bogdan, few things. First, what your current and future research plans are. Maybe you want to tell us a little bit about your current research lab and where you are, and maybe your collaborators that you are working with.
Yeah, so I'm currently based at Oxford Brookes University at the Visual AI Lab, led by Professor Fabio Pizzolin, who is the PI I'm working with, and the PI on the grant that funds me, which is a Liver Team grant. So it's this grant on machine theory of mind at the intersection of AI and neuroscience. And like the other PI in the grant is Professor Barbara Sahakian from Cambridge, who is a professor in psychiatry and neuroscience at Cambridge. And the other postdoc working with me, working with all of us on this grant is Dr. Christelle Langley, who is also at Cambridge and who is also working in neuroscience and psychology and psychiatry. And we are currently working on a bunch of topics. Like we are in the process of going to peer review for one survey. We are going through on machine theory of mind, so on theory of mind from the AI side and from the neuroscience side. I'm also thinking these days about trying to evaluate theory of mind in large language models, and also potentially trying to train language models on theory of mind tasks. We're also thinking about stuff like trying to get inspiration from human brains for like theory of mind architectures to implement in AI. Yeah, we might also be looking at stuff like brain data and how it might be used more directly for theory of mind. So there's a bunch of research lines. And in terms of what would help me, or like what collaborations might be interesting, like I'd be especially interested in for example, language modeling. Like those kinds of experiments tend to require quite a bit of compute, especially if you fine tune the language models, it might be better. But if I were to try to train from scratch, like there, I might really need some industrial collaborations. Otherwise, I'm also looking for. I'm still in the look for ideas, like just in general in about theory of mind, including from neuroscience. Like I'm constantly looking for like computational models from neuroscience. Yeah, and more generally, I'm just excited about AI safety and AI alignment. So yeah, have a pretty somewhat
Yeah.
wide range of interests, I would say.
You mentioned Bogdan few, minutes ago, uh, the importance of natural language in uh, this whole theory of mind framework, where uh, the AI agent can ask its human counterpart, or the human counterpart can ask the AI agent, "Hey, buddy, what do you think? What am I thinking right now? Or what am I trying to do?" And the AI to say, "Well, let me guess. I think, you're trying to do this, or you're trying to do that." Uh, and the person to say, "Why do you think that?" And uh, so, can you maybe elaborate, Bogdan, a little bit more about how you see language, natural language, playing a role both in training and in runtime in this human machine interaction, the role that natural language can play?
I mean, I think that natural language is probably the most natural modality we have. Like we humans, like we interact with each other mostly through language, it seems to me. So it kind of, and we also store a lot of knowledge, a lot of useful knowledge through language. So it seems to me like probably like the first powerful AIs will use a lot of language. Like it seems to me like it might be much more expensive to bypass any use of language if you want to get very, very powerful AI. So it kind of seems like a necessary component. It also seems to me like it might, like having an AI which understands and can use language could also help with explainabilities. Also on the like safety side, it could be pretty useful. In terms of training, like yeah, I'm a bit uncertain, but I think the arguments that I've mentioned in my slides are plausible, that even just scaling up current methods might take us all the way to human level. And I also think that evaluating theory of mind capabilities could also be like one way to monitor these capabilities. Like, it seems to me like one capability that you need for human level language processing is theory of mind. So if,
Yeah.
and it's also a pretty complicated capability to have. So it could kind of maybe serve kind of like some sort of fire alarm for more powerful language modeling. Like not just theory of mind, but like if you see theory of mind and if you see really robust mathematical capabilities and reasoning capabilities and so on, like maybe you need to start worrying more that you're really getting close to human level.
What would be a good way to evaluate the theory of mind models? Like, what are some ideas for evaluation approaches?
So I have to preface this by saying that I'm not an expert in natural language processing per se. So I have thought a bit about it, especially recently. And I think you could, like there are a few data sets already trying to evaluate where you just like describe a scenario in natural language. And then you ask also in natural language about the beliefs or the preferences of the people in those scenarios. So basically, as long as you translate any scene into description into natural language, and then you ask the questions into natural language and then expect the answers into natural language, kind of seems to me like you can probably translate most of theory of mind. Like you can probably frame most of theory of mind capabilities into uh, natural language processing. So just predicting the next words. So it seems like like language modeling seems like a very natural framework to model theory of mind. To me, at least, it seems very
If
natural.
Bogdan today team of software engineers and other folks, if they are working on designing autonomous systems, whether autonomous vehicles or any other form of such AI, what advice do you have for them, how they can become more interdisciplinary and add diverse skill sets, or any other piece of advice that you have for a team that is trying to solve those problems? What would you say to all those teams in terms of think about this, think about that, check this, check that out, add following kind of team members, so tell us a little bit about what your advice would be for any team out there that is trying to design autonomous systems that are going to interact with humans in one way or the other.
So I guess what I would say is like maybe just try to have at least a few discussions with people from other fields, and ideally with people who have uh, one foot in one field and one foot in another. For example, somebody who is first and foremost a social scientist, but who has also at least thought a bit about the machine learning side, for example. And I think that could be really valuable because you, at the very least, you could get some insights of like some problems you didn't know about or some approaches that you didn't know about, and like you can see afterwards if like there's scope for a more in-depth collaboration. But I think it's definitely very useful to think in multidisciplinary ways about all this, and like even just explore at the beginning at the very least, even if it's not gonna go super far, but at least having exploratory conversations, I think, is very important.
The last question that I'll have, Bogdan, for you, and thank you for being so generous with your time, is uh, who have influenced you the most, whether in your field or just in general in life? And if you want to mention any names or any books or work of people that have really influenced you in shaping your thinking, and would love to hear that.
So yeah, I'm just gonna preface that by saying that I'll probably forget somebody, so I apologize in advance for that. But I think like two major influences for me have been reading the book Superintelligence by Nick Bostrom, who is a philosopher at the University of Oxford. So that's been a huge influence for me thinking about like the longer term implications of AI and like of like potentially succeeding at solving AI, and like how we need to also consider like potential downsides, not just the good things which might come out of it. And then more on the in machine learning. In machine learning, I'm very inspired by Joshua Bengio and Jan LeCun and Geoffrey Hinton and Schmidt-Huber, who were like, I think they really provide an inspiration in the way that they just went through their work even when other people didn't believe that they were on the right track. Like they stuck with it for decades, and it panned out in the end. And I think that can be a really big lesson that, of course, you need to look at evidence from the outside that maybe you're on the wrong track, but you also kind of need to believe in the thing you work on. And sometimes, unfortunately, you need to stick with it even when others don't believe in it to get the biggest rewards.
Bogdan, sir, thank you for being so generous with your time. I learned a lot. I'm sure everybody who's going to watch, they're going to learn a lot. And people probably will reach out to you as well. So thank you. Thank you. Thank you. Thank you.
Thank you very much for the invitation. It was a lot of fun.